Hello there, and welcome to the Sleepy Library. It's lovely to have you here. Before we begin, I'd love to know where in the world you're watching from tonight. Perhaps you're tucked into bed with the curtains drawn, listening to the gentle sound of rain against the window. Or maybe you're on a train, watching the landscape slide by in the golden hour before sunset. Perhaps you're settled on a couch, with a warm drink beside you, a blanket across your lap, the day finally winding down to its peaceful conclusion. Wherever you are, whatever brought you here tonight, I hope you're comfortable, safe, and ready to gently let your thoughts wander through the quiet corridors of science and wonder. If you enjoy these relaxing explorations of our world and would like to hear more, a like and subscribe really helps this sleepy little channel continue its journey through the cosmos of knowledge. And to those of you already subscribed, those familiar faces who return again and again to these gentle evenings of learning, thank you. Truly, your support means more than you know. You make this possible, this little corner of the internet where we can slow down, breathe deeply, and explore the universe one fascinating fact at a time. Tonight, we're going to explore something both vast and intimate, something that touches every corner of our planet and every moment of our future. We'll wander through the science of global warming, not with alarm or urgency, not with the harsh glare of crisis, but with gentle curiosity and wonder. We'll discover how our atmosphere works like a delicate blanket, woven from invisible threads of molecules. We'll learn how tiny particles of carbon dioxide, each containing just 3 atoms, can hold the warmth of sunlight and change the temperature of an entire world. We'll trace the story of our changing climate as it's written in ancient ice cores pulled from Antarctic glaciers, in the temperature records of oceans that cover 2/3 of our planet, and in the slow dance of seasons that marks time across the continents. This is a story about connection, about how everything on Earth, from the smallest microbe to the largest whale, from tropical coral reefs to Arctic ice sheets, exists within a web of relationships so intricate that changing one thread affects the entire fabric. It's a story about energy and chemistry, about physics and biology, about human choices and natural consequences. And perhaps most importantly, it's a story that's still being written, with chapters yet to come that depend on what we do now in these crucial years. So settle in. Let your shoulders drop away from your ears. Unclench your jaw if it's tight. Take a deep breath, filling your lungs completely, and then release it slowly, letting tension flow out with the exhale. We have time tonight. No rush, no pressure. Just a gentle journey through one of the most important scientific stories of our age, told in a way that invites calm rather than anxiety, understanding rather than fear. And let's begin this journey together, one soft fact at a time, like stones placed carefully across a stream, each one leading naturally to the next. The story of global warming begins not with catastrophe, but with something beautifully simple, something so familiar we rarely stop to think about it. Sunlight. Every morning as dawn breaks across whichever part of the earth faces the sun, light begins its journey toward us. This light has traveled across 93 million miles of space, a journey that takes about 8 minutes and 20 seconds. It crosses the cold vacuum where nothing exists to slow it down, where silence is absolute because there's no air to carry sound waves, where temperatures hover near absolute zero except where starlight touches. And then this light, this electromagnetic radiation, carrying energy from nuclear fusion reactions in the sun's core, reaches our atmosphere. Some of it never makes it to the surface. About 30% bounces back immediately, reflected by clouds, by ice and snow, by the pale surfaces of deserts and concrete cities. This reflected light is what makes Earth visible from space, what gives our planet its characteristic blue and white appearance when seen from the moon or from distant spacecraft. But 70% of the sunlight does reach the ground. It streams through the atmosphere, warming the air as it passes. It strikes the surface of the ocean and penetrates into the depths, warming the water. It falls on forests where leaves absorb it to power photosynthesis. It heats soil and rock. It melts ice. It evaporates water. In countless ways, visible and invisible, this solar energy powers every process on Earth. The weather is driven by uneven heating between the equator and poles. Ocean currents flow because of temperature differences. Plants grow. Animals move. Entire ecosystems function because of the steady flow of energy from our star. The Earth absorbs this energy and then, like all warm objects in the universe, radiates heat back towards space. But this outgoing energy is different from the incoming sunlight. The sun, burning at about 5,500 degrees Celsius at its surface, emits primarily visible light and shorter wavelengths like ultraviolet. The Earth, at much lower temperatures, averaging about 15 degrees Celsius, emits primarily infrared radiation, what we perceive as heat. You can feel this infrared radiation yourself. Hold your hand over a sun-warmed rock on a summer evening after the sun has set. The rock feels warm because it's emitting infrared radiation that your skin absorbs. Now here's where the story becomes interesting. If all this infrared heat simply escaped back into space with nothing impeding it, Earth would be much colder. Scientists have calculated that without any atmosphere at all, or with an atmosphere that was completely transparent to infrared radiation, Earth's average temperature would be around -18 degrees Celsius. That's well below the freezing point of water. Oceans would be solid ice, if they existed at all. Life as we know it would be impossible. The delicate chemistry that makes cells function, that allows DNA to replicate, that enables all the complex processes of biology, requires liquid water. A frozen world is a sterile world, but we don't live on a frozen world. We live on a planet with an average temperature of about 15 degrees Celsius, a full 33 degrees warmer than it would be without the greenhouse effect. This warmth, this habitability, this gift of liquid water and moderate temperatures, all comes from the atmosphere's ability to trap some of the outgoing infrared radiation. The atmosphere does this through certain gases, molecules with specific properties that allow them to absorb infrared light. Not all gases can do this. Nitrogen and oxygen, which together make up 99% of the atmosphere, are largely transparent to infrared. They don't interact with it significantly. But trace gases, present in much smaller amounts, do interact. And it's these trace gases, these greenhouse gases, that make our planet warm enough for life. Think of it like this. The atmosphere acts like a blanket, but not a solid blanket like wool or cotton. It's more like a selective filter, one that lets visible light pass through easily in both directions, but catches and holds infrared radiation. Sunlight streams in without hindrance. But when Earth tries to radiate heat back to space, some of that heat gets intercepted, absorbed by greenhouse gas molecules, and re-emitted in random directions, including back toward the surface. The result is that energy accumulates in the lower atmosphere and at the surface, warming them beyond what they would be if heat could escape freely. This is the greenhouse effect, and it's named after greenhouses because early scientists thought greenhouses worked the same way, trapping heat behind glass. They don't actually. Greenhouses work mainly by preventing warm air from rising and being carried away by wind, but the name stuck. The atmospheric greenhouse effect is real, measurable, and essential for life. It's been operating for billions of years, maintaining Earth in a temperature range that allows complex chemistry, liquid water, and the emergence of life. The problem, the challenge we face now, isn't the greenhouse effect itself. The greenhouse effect is what makes our planet habitable. The problem is that we're enhancing it, strengthening it, adding more and more greenhouse gases to the atmosphere through our activities. We're thickening the blanket. And just as adding more blankets to your bed makes you warmer, adding more greenhouse gases to the atmosphere makes the planet warmer. To understand how this works, we need to meet the molecules that make it all possible, the key players in the greenhouse effect. Each of these gases has a story, a role, a particular way it interacts with energy and influences climate. Let's start with carbon dioxide, the most famous greenhouse gas, the one that appears most often in news reports and scientific papers about climate change. A carbon dioxide molecule is elegantly simple in structure. It consists of one carbon atom in the center, with two oxygen atoms bonded to it, one on each side, forming a straight line. If you could see it magnified enormously, it would look like three spheres in a row, the center one slightly smaller than the outer two. This linear structure gives carbon dioxide its infrared absorbing properties. When infrared radiation passes by a carbon dioxide molecule, the molecule can absorb photons of specific wavelengths, those that match its natural vibration frequencies. Think of it like a tuning fork that resonates when struck at just the right pitch. Carbon dioxide resonates with certain wavelengths of infrared light. When it absorbs this energy, the molecule begins to vibrate more intensely. The carbon atom moves back and forth along the axis connecting the oxygen atoms. Or, the oxygen atoms bend toward and away from the axis, like arms waving. These vibrations represent stored energy, heat captured from the infrared radiation that was trying to escape to space. But molecules don't hold this energy forever. After a brief moment, typically less than a second, the vibrating molecule releases the energy by emitting a new infrared photon. This emitted photon flies off in a random direction. It might go upward towards space, or sideways, or downward toward Earth's surface. On average, about half the re-emitted infrared goes back down. This downward radiation warms the surface and lower atmosphere, energy that would have escaped to space, but instead gets recycled back into the climate system. The truly remarkable and problematic aspect of carbon dioxide is its persistence. Once released into the atmosphere, a carbon dioxide molecule doesn't break down or disappear quickly. There's no natural chemical reaction that destroys it in the air. Instead, carbon dioxide leaves the atmosphere only by being absorbed into something else. Dissolved into ocean water, taken up by plants during photosynthesis, or incorporated into soil. These processes, collectively called carbon sinks, remove carbon dioxide, but they work slowly. About half of the carbon dioxide emitted by human activities gets absorbed within a few decades, split roughly between oceans and land ecosystems. But the other half lingers much longer. Some remains in the atmosphere for centuries. Some will still be there thousands of years from now, because the very slow processes of ocean mixing and rock weathering are required to remove it permanently. This long residence time means carbon dioxide accumulates. Every year that we emit more than natural processes can absorb the atmospheric concentration increases. It's like a bathtub with the faucet running faster than the drain can empty. The water level rises. In Earth's case, the carbon dioxide level rises. Before the Industrial Revolution, before humans began burning fossil fuels on a massive scale, the concentration of carbon dioxide in the atmosphere hovered around 280 parts per million. This was the baseline for at least 10,000 years through the entire development of human civilization. It was the concentration during the time of ancient Egypt and Rome, during the Middle Ages, during the Renaissance. This level was maintained by the natural carbon cycle, a complex exchange of carbon between atmosphere, oceans, land, and living things. Plants would absorb carbon dioxide and release oxygen. Animals would breathe oxygen and release carbon dioxide. Dead plants and animals would decompose, returning carbon to the soil or ocean. Occasional volcanic eruptions would belch carbon dioxide into the air. Weathering of rocks would slowly lock carbon away in minerals. The system was roughly balanced, self-regulating over long timescales. Then, in the late 1700s, everything changed. Humans discovered that coal, that black rock, formed from ancient forests, compressed and heated deep underground over millions of years, could be burned to release enormous amounts of energy. This energy could power steam engines, drive machinery, heat buildings, forge steel. The Industrial Revolution began in Britain and spread worldwide, transforming societies from agricultural to industrial, from rural to urban, from human and animal power to machine power. But this transformation had a hidden cost. Coal is mostly carbon that was removed from the atmosphere hundreds of millions of years ago when plants pulled carbon dioxide from the air. And that carbon eventually became buried and transformed into coal. Burning it releases that ancient carbon back into the atmosphere as carbon dioxide. It's like opening a locked vault and pouring its contents into the air. Later, petroleum oil was discovered and exploited, first for kerosene lamps, then for gasoline to power automobiles, then for diesel fuel, aviation fuel, heating oil, and countless other uses. Natural gas followed, piped into homes and businesses, burned in power plants and factories. Each of these fossil fuels is hydrocarbon, chains or rings of carbon and hydrogen atoms. When burned in the presence of oxygen, the carbon combines with oxygen to form carbon dioxide. The hydrogen combines with oxygen to form water vapor, and energy is released as heat and light. This energy is what we've harnessed to build modern civilization. But the carbon dioxide is an inevitable byproduct, exhaust from the global engine of industrial society. The numbers tell a stark and accelerating story. In the year 1958, a scientist named Charles David Keeling began a monitoring program at the Mauna Loa Observatory in Hawaii, a facility perched on the slopes of a volcano in the middle of the Pacific Ocean, far from major sources of pollution, an ideal location for measuring the background concentration of atmospheric gases. When Keeling's instruments began recording data, the concentration of carbon dioxide stood at 315 parts per million. This was already elevated above the pre-industrial baseline of 280, reflecting more than a century of industrial emissions, but it was just the beginning. Year after year, Keeling's measurements showed the same pattern. Carbon dioxide concentrations rising steadily, with a seasonal oscillation overlaid on the upward trend. Each spring and summer in the Northern Hemisphere, where most of Earth's landmass exists, plants would grow and photosynthesize vigorously, pulling carbon dioxide from the atmosphere. The concentration would dip slightly. Then, each autumn and winter, plants would die back or go dormant. Respiration and decomposition would dominate over photosynthesis, and carbon dioxide would rise. This seasonal breathing of the planet, this annual cycle of growth and dormancy, created a sawtooth pattern in the data. But the overall trend was unmistakable. Up, 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 year after year, decade after decade. By the turn of the millennium, in the year 2000, the concentration had reached 369 parts per million. By 2010, it was 389. By 2020, 414. And in 2024, the most recent data available, it reached 422.8 parts per million, a new record high, unprecedented in human history. The increase during 2024 alone was 3.75 parts per million, the largest single-year jump ever recorded in the Keeling curve, as this data series has come to be known. To put this in perspective, scientists can measure carbon dioxide concentrations from ancient times by analyzing air bubbles trapped in Antarctic ice. As snow falls in Antarctica, it gradually compresses into ice, and tiny pockets of air get sealed inside, preserving samples of the atmosphere from when that snow fell. By drilling deep ice cores and analyzing these air bubbles, researchers have reconstructed atmospheric carbon dioxide levels going back 800,000 years. The data reveals a clear pattern. During ice ages, when massive glaciers covered much of North America and Europe, carbon dioxide concentrations dropped to around 180 parts per million. During warmer interglacial periods, like the one we're in now, they rose to about 280 parts per million. The concentration oscillated between these bounds, driven by natural cycles related to Earth's orbit and axial tilt, cycles that take tens of thousands of years to complete. Never, in 800,000 years, did carbon dioxide exceed 300 parts per million. Not during the warmest interglacials, not during any. Climatic event recorded in the ice. 300 was an upper limit, a ceiling that natural processes never breached. Until now. The current level of 422.8 parts per million is 50% higher than the natural maximum. It's a concentration that hasn't existed since the Pliocene epoch, more than 3 million years ago, when Earth was significantly warmer, sea levels were tens of meters higher, and the Arctic had forests instead of ice. The rate of increase is also unprecedented. The fastest natural increases in carbon dioxide, occurring as Earth emerged from ice ages, happened at a pace of about 10 to 15 parts per million per 1,000 years. The current increase is happening at roughly 20 to 30 parts per million per decade. That's 100 to 200 times faster than the natural rate. In geological terms, this is essentially instantaneous change, a spike so sharp and sudden that it appears vertical on graphs covering millennia. What does this mean for temperature? The relationship between carbon dioxide and temperature is direct, measurable, and well understood through both physics and observation. As greenhouse gas concentrations increase, they trap more infrared radiation. More heat accumulates in the atmosphere and oceans. The planet warms. This isn't speculation or modeling. It's basic physics, confirmed by thermometers around the world, by satellite measurements, by ocean temperature probes, by countless independent lines of evidence. Over the last century, from the late 1800s to the present, average global temperatures have risen by approximately 1.2 degrees Celsius compared to pre-industrial times. The warming was gradual at first, about 0.1 degrees per decade through much of the 20th century, but it has accelerated. Since the 1970s, the rate of warming has been approximately 0.2 to 0.3 degrees per decade, 2 to 3 times faster than the earlier rate. 1.2 degrees might not sound like much. It's barely noticeable if a room's temperature changes by that amount. but climate systems are exquisitely sensitive to average temperature changes. The difference between an ice age and an interglacial period, between glaciers covering Canada and a temperate climate there, is only about 4 to 7 degrees of global average temperature change. A shift of 1 degree is significant. 2 degrees is transformative. 3 or 4 degrees would reorganize global climate patterns in ways that challenge human societies and natural ecosystems. The warming is not uniform across the planet. Some regions are heating faster than others. The Arctic, that vast region surrounding the North Pole, is warming at more than twice the global average rate, a phenomenon scientists call Arctic amplification. This happens because of feedback loops. As Arctic sea ice melts, it exposes dark ocean water beneath. Ice is highly reflective, with an albedo of 70 to 80%, meaning it bounces most sunlight back to space. Ocean water is much darker, absorbing 80 to 90% of incoming sunlight and converting it to heat. This warms the ocean further, which melts more ice, which exposes more dark water, which absorbs more heat. The cycle reinforces itself, accelerating Arctic warming beyond what greenhouse gases alone would cause. Similar amplification occurs on land, where snow cover is disappearing. Dark forests, tundra, and bare ground absorb more sunlight than snow-covered surfaces. As snow retreats, more heat gets absorbed, warming the land, which makes snow melt even earlier the following year. These are what scientists call positive feedback loops. Not positive in the sense of being good, but positive in the mathematical sense of amplifying the original change. They're self-reinforcing cycles that push the system further in the direction it's already moving. The years since the late 1990s have been remarkable in the temperature record. Of the 10 warmest years ever recorded globally, 9 have occurred since 1998. The decade from 2015 to 2024 was the warmest decade in recorded history, and likely the warmest in many thousands of years based on paleoclimate evidence. In 2024, global average temperature reached approximately 1.55 degrees Celsius above pre-industrial levels, a milestone that climate scientists have warned about for years. Every month set records. Every season was anomalously warm. The evidence is not ambiguous. Earth is warming, rapidly and consistently. But carbon dioxide, despite being the most important long-lived greenhouse gas, is not the only one we need to understand. Other gases also trap heat, and some are far more potent on a molecule-by-molecule basis. Methane is the second most important greenhouse gas in terms of its contribution to current warming. A methane molecule consists of one carbon atom bonded to 4 hydrogen atoms, arranged in a tetrahedral shape like a pyramid with a triangular base. This structure gives methane its infrared absorption properties. But methane is special because it's extraordinarily effective at trapping heat. Over a 100-year timescale, one molecule of methane traps about 28 times more heat than one molecule of carbon dioxide. Over shorter timescales, like 20 years, methane is even more potent, about 80 times stronger than carbon dioxide, because it takes time for methane to break down in the atmosphere. Fortunately for us, methane doesn't persist as long as carbon dioxide. Atmospheric chemical reactions gradually destroy methane molecules. Hydroxyl radicals, reactive molecules formed from water vapor and ozone, attack methane and break it down into carbon dioxide and water vapor. The average lifetime of a methane molecule in the atmosphere is about 12 years. This means that if we reduced methane emissions, atmospheric concentrations would decline relatively quickly, providing near-term climate benefits. It's one of the few levers we can pull for relatively fast results. Methane comes from numerous sources, both natural and human-caused. Natural wetlands are the largest natural source. In swamps, bogs, and marshes, where water saturates the soil, organic matter decomposes in low oxygen conditions, and certain microbes called methanogens produce methane as a metabolic byproduct. This process has been happening for millions of years, cycling methane through the atmosphere at rates that natural sinks could balance. But human activities have greatly increased methane emissions. Rice paddies, which cover millions of hectares worldwide, create wetland-like conditions where methanogens thrive. Livestock, particularly cattle and sheep, are major methane sources. These ruminant animals have multi-chambered stomachs containing methane-producing microbes that help them digest tough plant material like grass and hay. As the animals digest their food, they belch methane, releasing it directly into the atmosphere. With approximately 1.5 billion cattle and over 1 billion sheep worldwide, livestock contribute about 32% of human-caused methane emissions. Landfills release methane as organic waste decomposes in oxygen-poor conditions under layers of trash and soil. Old landfills can continue emitting methane for decades after they close. Some modern landfills capture this methane and burn it for energy, but many don't. The fossil fuel industry is another major methane source. Natural gas is primarily methane, typically 85 to 95% methane, with small amounts of other hydrocarbons and trace gases. Whenever natural gas leaks from wells, pipelines, processing facilities, or distribution networks, that methane enters the atmosphere. Oil wells also release methane, either dissolved in the petroleum or as associated gas that comes up alongside the oil. Some of this gas gets burned off in flares, converting it to carbon dioxide. But unburned methane can escape during these processes. Coal mining releases methane that was trapped in coal seams underground. As miners extract coal, they ventilate shafts to prevent dangerous methane buildup, releasing it to the atmosphere. The amount of methane in the atmosphere has more than doubled since pre-industrial times, rising from approximately 722 parts per billion in the 1700s to over 1922 parts per billion by 2023. Like carbon dioxide, this increase is entirely due to human activities. The natural sources remain roughly constant, but we've added new sources on top of them. Then there's nitrous oxide, another greenhouse gas with substantial warming potential and long atmospheric lifetime. A nitrous oxide molecule consists of two nitrogen atoms bonded to one oxygen atom, arranged in a linear chain. This gas is approximately 300 times more effective at trapping heat than carbon dioxide over a 100-year period. Though present in much smaller concentrations than carbon dioxide or methane, its potency makes it a significant contributor to warming. Nitrous oxide is primarily released through agricultural activities, specifically the use of nitrogen-based fertilizers. Modern agriculture depends on these fertilizers to boost crop yields, replacing nitrogen that plants remove from soil. When farmers apply these fertilizers, whether synthetic chemicals like ammonium nitrate or organic materials like manure, microbes in the soil convert some of that nitrogen into nitrous oxide through biochemical processes called nitrification and denitrification. The nitrous oxide then diffuses up through the soil and into the atmosphere. The gas is also produced during fossil fuel combustion, particularly from vehicles and power plants, and from certain industrial processes like adipic acid and nitric acid production, both used in manufacturing nylon and other chemicals. The combustion of fossil fuels at high temperatures causes some atmospheric nitrogen to react with oxygen, forming various nitrogen oxides, including nitrous oxide. Since the Industrial Revolution began in the late 1700s, nitrous oxide concentration in the atmosphere has increased by approximately 20%, from 270 parts per billion to 337 parts per billion by 2023. While this sounds like a small change, and nitrous oxide is present in trace amounts compared to major atmospheric gases like nitrogen and oxygen, its extreme potency as a greenhouse gas means it has an outsized effect on warming. Additionally, nitrous oxide has a very long atmospheric lifetime, averaging about 120 years. This means emissions today will continue influencing climate for more than a century. Then we have water vapor, the most abundant greenhouse gas in the atmosphere, and one that operates differently from the others we've discussed. Water vapor concentration varies greatly depending on location, weather conditions, and most importantly, temperature. A cubic meter of air can hold only a few grams of water vapor when temperatures are near freezing, but it can hold dozens of grams when temperatures are tropical. Unlike carbon dioxide or methane, which we can add directly to the atmosphere through our activities, and which persist for years or decades, water vapor cycles through the atmosphere in a matter of days or weeks. It evaporates from oceans, lakes, soil, and plants. It condenses into clouds. It precipitates as rain or snow. The amount present at any given time is determined primarily by temperature, because warm air can hold exponentially more moisture than cold air. This creates a powerful feedback effect. As carbon dioxide, other long-lived greenhouse gases warm the planet, more water evaporates from oceans and land surfaces. This additional water vapor, itself a greenhouse gas, traps even more heat. The warming intensifies. Then this enhanced warming causes still more evaporation. It's another positive feedback loop, one of the strongest in the climate system. Scientists estimate that water vapor feedback amplifies the warming from carbon dioxide and other greenhouse gases by roughly a factor of 2. If carbon dioxide alone would cause 1 degree of warming, the water vapor feedback makes it closer to 2 degrees. Clouds complicate this picture because they can both warm and cool the planet, depending on their type, altitude, and properties. Low-altitude clouds, like the puffy cumulus clouds of summer afternoons, tend to reflect sunlight and cool the surface. High-altitude cirrus clouds, thin and wispy, tend to trap infrared radiation and warm the surface. The net effect of clouds on climate is one of the most uncertain aspects of climate science. Not because scientists don't understand clouds, but because clouds are incredibly complex and vary greatly in space and time. Small changes in cloud properties or distribution can have significant effects on the energy balance. Current research using satellites, ground observations, and computer models continues to refine our understanding of how clouds will respond to warming, and how that response will feed back into future warming. All these gases together, carbon dioxide, methane, nitrous oxide, and water vapor, along with smaller contributions from other industrial gases like hydrofluorocarbons and sulfur hexafluoride, have increased what scientists call radiative forcing. This is a measure of how much the energy balance at the top of the atmosphere has changed. Since pre-industrial times, the increase in greenhouse gases has caused approximately 2.9 watts per square meter of additional heating effect globally. To put that in perspective, it's roughly equivalent to turning on a holiday light bulb and leaving it on continuously over every square meter of Earth's surface. Multiply that by the 500 trillion square meters of Earth's surface, and you get an enormous amount of extra energy being trapped in the climate system. Where does all this energy go? Most of it goes into the ocean. More than 90% of the excess heat trapped by greenhouse gases since the 1970s has been absorbed by the ocean, which has an immense capacity to store heat because water has a high specific heat capacity and the ocean is vast and deep. This has slowed atmospheric warming, buffering the temperature rise that we experience on land and in the air. If the ocean weren't absorbing this heat, atmospheric temperatures would have risen much more dramatically, much faster. In a sense, the ocean has been protecting us from the full consequences of our emissions. But this protection comes at a cost to the ocean itself, costs we'll explore shortly. And the atmospheric warming, though moderated by ocean heat uptake, is still substantial and accelerating. The enhanced greenhouse effect is not a future concern or a theoretical possibility. It's happening now, measured by instruments around the world, confirmed by independent research teams, visible in the data from satellites, weather stations, ocean buoys, and countless other sensors monitoring Earth's vital signs. The total warming effect from all greenhouse gases added by humans to the atmosphere has increased by 51% since 1990. The warming effect from carbon dioxide alone has increased by 42% in that same period. These are not small numbers. They represent a fundamental alteration of Earth's energy balance, a forcing that pushes the climate system out of the relatively stable state it had maintained for thousands of years. Now, you might be wondering, if greenhouse gases have been increasing steadily for more than a century, and the enhanced greenhouse effect is real and measurable, why isn't everyone experiencing dramatically warmer weather every single day? Why do cold snaps still happen? Why do some winters still bring heavy snow? The answer lies in understanding the difference between weather and climate, and in recognizing that climate change doesn't mean uniform warming everywhere all the time. Weather is what happens day to day, the specific conditions of temperature, humidity, wind, clouds, and precipitation at a given location and time. Climate is the average of weather over long periods, typically 30 years or more, across large regions. Weather is inherently chaotic and variable. Even a small perturbation can cause large changes in weather patterns days or weeks later, making precise weather forecasting beyond about 10 days extremely difficult. Climate, being an average over time and space, is much more predictable. We can't predict whether it will rain on a specific day months from now, but we can predict with confidence that the planet will be warmer on average next decade than it was last decade if greenhouse gas emissions continue increasing. Global warming doesn't eliminate cold weather or snow. It shifts the probabilities. Record high temperatures become more common. Record low temperatures become less common. The frequency and intensity of heat waves increase. The coldest nights of winter aren't as cold on average as they used to be. Growing seasons lengthen. First frost comes later in autumn. Last frost comes earlier in spring. These shifts are subtle year to year, sometimes masked by natural variability, but they become clear when you analyze decades of data across large regions. And importantly, climate change affects different places differently. The Arctic warms faster than the tropics. Continental interiors warm faster than coastal areas. Nighttime temperatures increase faster than daytime temperatures. Winters warm faster than summers in many regions. These patterns emerge from the physics of how energy moves through the climate system, how ocean currents redistribute heat, how ice and snow reflect light, how elevation affects temperature, how latitude determines the angle of incoming sunlight. Global average temperature is useful for tracking overall trends, but it masks significant regional variations. Now let's follow the journey of this additional heat, trace its path through the Earth system, and see how it reshapes our world in both subtle and dramatic ways. We'll start where the most visible and perhaps the most iconic changes are occurring, in the world's ice. The first and most visible consequence of global warming, the change that perhaps captures public imagination more than any other, is the transformation of ice. Ice, in its various forms, is one of Earth's most sensitive indicators of temperature change, responding quickly and visibly to even small shifts in climate. When the world warms, ice melts. This might seem obvious, almost tautological, a simple cause and effect that needs no explanation. But the implications ripple through every aspect of the climate system, touching weather patterns, ocean circulation, sea level, freshwater supplies, ecosystems, and human societies in ways both direct and indirect. Let's start with glaciers, those magnificent rivers of ice that flow slowly down mountainsides in every major mountain range on Earth. From the Andes to the Alps, from the Himalayas to the Rockies, from Alaska to New Zealand, glaciers have existed for thousands of years, growing and shrinking with natural climate cycles, but always persisting as defining features of mountain landscapes. Glaciers form in places where winter snowfall exceeds summer melting, where the cold season deposits more frozen water than the warm season can remove. Year after year, snow accumulates. The weight of new snow compresses older snow beneath it. Air gets squeezed out. The compressed snow transforms into firn, a granular transitional state between snow and ice. With more compression, over decades and centuries, firn becomes glacial ice, dense and blue, and capable of flowing under its own weight, like an extremely slow-moving viscous fluid. The ice flows downhill, pulled by gravity, sometimes moving only centimeters per year, sometimes moving meters per day in the fastest flowing glaciers. As it flows, it carves valleys, plucks rocks from bedrock, and carries debris. Eventually, the glacier reaches elevations or latitudes warm enough that melting exceeds accumulation. The ice melts, releasing water into streams and rivers. This is the terminus, the toe of the glacier, the point where ice transforms back into liquid water after its long journey from the high snowfields. For thousands of years, glaciers existed in dynamic equilibrium, advancing during cooler periods when snowfall was heavy or summers were mild, retreating during warmer periods, but maintaining their overall presence. Indigenous peoples living in mountain regions knew these glaciers as permanent features, sources of water, obstacles to travel, objects of spiritual significance. Early European explorers and climbers encountered them and mapped them. Scientists began studying them systematically in the 19th century, measuring their extent, tracking their movements, investigating the physics of ice flow. But beginning in the early 1900s and accelerating rapidly in recent decades, glaciers around the world have been retreating, losing mass, in many cases disappearing entirely. The World Glacier Monitoring Service, an international organization that coordinates the collection of standardized glacier data from around the world, maintains records of reference glaciers that have been consistently monitored for decades. Their data paints a clear and concerning picture. During the 1980s, these reference glaciers lost the equivalent of 171 millimeters of liquid water per year, averaged across their surface area. This means that if you took all the ice lost and melted it, it would form a layer of water 171 millimeters deep, covering the entire glacier surface. That's already significant ice loss, but it was just the beginning. By the 1990s, annual losses had increased to 460 millimeters. In the 2000s, 500 millimeters, and between 2010 and 2018, the loss rate reached 850 millimeters per year. That's a quintupling of ice loss rate in just 3 decades, from the 80s to the 2010s. Glaciers that took centuries to form, accumulating snow layer by patient layer, winter after winter, are vanishing within human lifetimes, within single careers of the scientists studying them. In Alaska, the transformation is particularly dramatic. The Pedersen Glacier, located in the Kenai Mountains near Ayalik Bay, serves as a striking visual example of this change. Historical photographs from 1917 show the glacier descending all the way to sea level, its terminus reaching Ayalik Bay and carving icebergs into a marginal lake. The glacier dominated the landscape, a massive presence of ice filling the valley. By 2005, just 88 years later, the glacier had retreated kilometers up the valley. The lake it had dammed had drained. The sediment that had been trapped behind the ice had been exposed and colonized by vegetation. What was once a landscape of ice and cold water had transformed into a small grassland with scattered shrubs. Side-by-side comparison of the 1917 and 2005 photographs shows a transformation so complete that they barely seem like the same place. This pattern repeats across Alaska and around the world. Montana's Glacier National Park had approximately 150 glaciers when it was established in 1910. Now it has fewer than 30, and many of those remaining are small remnants that may not persist much longer. The glaciers of the European Alps have lost approximately half their volume since the 1850s. The glaciers of the Himalayas, often called the Third Pole because they contain the largest volume of ice outside the polar regions, are retreating rapidly, with serious implications for the millions of people downstream who depend on glacial meltwater. This matters profoundly because glaciers are natural reservoirs, storing water frozen during wet seasons and releasing it gradually during dry seasons. In many parts of the world, particularly in South America, Central Asia, and parts of North America, communities depend directly on glacial meltwater for drinking water, for irrigating crops, for generating hydroelectric power. Rivers fed by glacial melt provide reliable water flow even during summer and autumn when rainfall is scarce. As glaciers shrink, this water supply becomes less predictable and less abundant. In Peru, for example, the tropical glaciers of the Cordillera Blanca provide essential dry season water flow to rivers that supply Lima, a city of nearly 10 million people situated on a desert coast. These tropical glaciers, existing near the equator only because of high elevation, are among the most sensitive to warming. They're shrinking faster than glaciers at higher latitudes. Some projections suggest they could lose 70 to 80% of their current mass by the end of the century, leaving Lima and other cities facing severe water scarcity. The Himalayas present an even larger scale challenge. The glaciers and snowpack of the Hindu Kush Himalaya region feed 10 of Asia's largest river systems, including the Indus, Ganges, Brahmaputra, Mekong, and Yellow rivers. These rivers sustain more than 1 billion people across multiple countries. Changes in the timing and volume of glacial meltwater will affect agriculture, drinking water supplies, hydropower generation, and ecosystems across a vast region. Initially, as glaciers melt, rivers can actually see increased flow, a temporary abundance as the ice releases water it stored over centuries. But this is a one-time withdrawal from a finite account. Once the glaciers are gone, only seasonal snow and rainfall will feed these rivers. The flow will become more variable, less reliable, lower overall. This transition from ice-buffered to snow and rain-buffered hydrology represents a fundamental transformation of water systems that billions of people depend on. But the most dramatic ice changes, the transformations with the gravest implications for global sea level, are occurring not in mountain glaciers, but at the poles, in the vast ice sheets of Greenland and Antarctica. These are not mere glaciers, not valleys filled with flowing ice, but continental-scale masses of frozen water, kilometers thick in their centers, containing volumes of ice difficult to comprehend. The Greenland ice sheet covers approximately 1.7 million square kilometers, an area about 3 times the size of France. At its thickest point, the ice is more than 3 kilometers deep. 3,000 meters of compacted snow and ice accumulated over hundreds of thousands of years. This single ice sheet contains enough frozen water to raise global sea levels by approximately 7 meters if it were to melt completely. 7 meters is roughly 23 feet, enough to submerge most coastal cities, to redraw coastlines dramatically, to displace hundreds of millions of people. Scientists monitor Greenland's ice sheet using satellites that measure tiny changes in Earth's gravitational field, changes that occur when mass redistributes on the planet's surface. The GRACE satellites, launched in 2002, and their successor GRACE follow-on, launched in 2018, have revealed unambiguous and accelerating ice loss from Greenland. Between 1992 and 2001, Greenland was losing approximately 34 billion tons of ice per year. That sounds like an enormous amount, and it is, but it was relatively stable, perhaps even within the range of natural variability. But then the ice loss accelerated. Between 2012 and 2016, Greenland was shedding 247 billion tons of ice per year, a 7-fold increase in just 2 decades. This ice loss occurs through 2 primary mechanisms. Surface melting is the first and most obvious. As air temperatures rise, summer melting intensifies and extends later into the season and to higher elevations. Meltwater streams across the ice surface, sometimes collecting in vivid turquoise pools, eventually draining off the edges, or, more concerning, draining down through cracks and crevasses to the bedrock beneath the ice. When meltwater reaches the bottom of the ice sheet, it acts as a lubricant, allowing the ice to slide more easily toward the ocean. This can accelerate ice flow, hastening the delivery of ice to the coast, where it can carve into icebergs and melt in warmer ocean water. The second mechanism is ice discharge, the process where glaciers flowing from the interior of the ice sheet reach the coast and break apart, carving icebergs that float away and eventually melt. Some of Greenland's outlet glaciers have accelerated dramatically in their flow speed, delivering more ice to the ocean than they did decades ago. Jakobshavn Glacier, one of Greenland's largest and fastest-moving glaciers, roughly doubled its flow speed between the 1990s and 2000s. Antarctica, the frozen continent at Earth's southern pole, contains even more ice than Greenland, approximately 26.5 million cubic kilometers of it, enough to raise global sea levels by about 58 meters if it all melted. For a long time, scientists thought Antarctica might be relatively stable, perhaps even gaining mass as warming brought slightly more snowfall to the frigid interior. But recent data has dispelled this notion. Antarctica is losing ice, and the rate of loss is accelerating. Between 1992 and 2001, Antarctica was losing approximately 51 billion tons of ice per year. Between 2012 and 2016, the loss rate had nearly quadrupled to 199 billion tons per year. Most of this loss is occurring in West Antarctica, where geography creates special vulnerabilities. Unlike East Antarctica, where most of the ice sits on bedrock that's above sea level, much of West Antarctica's ice rests on bedrock that lies below sea level, sometimes hundreds of meters below. The ice sheets extend as ice shelves vast floating platforms of ice extending from the coast, still connected to the grounded ice but floating on the ocean. These ice shelves act as buttresses, providing back pressure that slows the flow of grounded ice toward the sea. But when ocean temperatures rise, when warmer currents circulate beneath these ice shelves, they melt from below. This thinning weakens them. Eventually, they can crack and break apart. When an ice shelf collapses, it's like removing a cork from a bottle. The grounded ice behind it accelerates, flowing more rapidly toward the ocean, adding its mass to the sea and raising sea level. One glacier in West Antarctica has captured particular attention from scientists and has earned the ominous nickname the Doomsday Glacier. Its official name is Thwaites Glacier, and it's roughly the size of the state of Florida or Great Britain, an immense river of ice flowing from West Antarctica's interior toward the Amundsen Sea. Thwaites acts as a keystone in the region's ice architecture, helping to hold back a larger portion of the West Antarctic ice sheet. Its position and characteristics make it critically important for future sea level. Research expeditions to Thwaites, including underwater robotic missions beneath its floating ice shelf, have revealed concerning changes. The glacier is thinning. Warm ocean water is circulating beneath its ice shelf, melting it from below at rates much higher than previously thought. The grounding line, the point where the glacier lifts off bedrock and begins floating, is retreating. In some areas, the glacier is losing contact with underwater ridges that had helped stabilize it, allowing it to flow faster toward the sea. Computer models simulating Thwaites' future behavior suggest it may have already passed a threshold beyond which its retreat becomes self-reinforcing and difficult or impossible to stop on human timescales. As it retreats into deeper water, more of its ice base becomes exposed to warm ocean currents. This accelerates melting, which causes more retreat, which exposes more ice to warm water. The positive feedback loop could lead to collapse of large sections of Thwaites and neighboring glaciers within decades or centuries. If Thwaites and its associated ice were to be lost to the ocean, global sea level could rise by more than 3 meters, approximately 10 feet. This wouldn't happen overnight. Ice sheet collapse is a process that unfolds over decades to centuries. But once triggered, it may be unstoppable. With any technology we currently possess or can envision, we can't refreeze an ice sheet. We can't buttress it with engineering solutions at this scale. The only intervention is prevention, stopping the warming before critical thresholds are crossed. Then there's Arctic sea ice, that floating cap of frozen ocean that forms each winter in the Arctic Ocean and partially melts each summer. This ice is different from glaciers and ice sheets because it floats on water rather than sitting on land. When sea ice melts, unlike land ice, it doesn't directly raise sea level, for the same reason that ice cubes melting in a full glass of water don't cause it to overflow. The ice was already displacing its weight in water when floating. But Arctic sea ice plays a crucial role in regulating global climate through what scientists call the albedo effect, the interaction between ice and sunlight we mentioned earlier. Fresh snow and ice have an albedo of 70 to 85%, meaning they reflect most incoming sunlight back to space. The energy in that reflected light never gets converted to heat in Earth's climate system. Dark ocean water, by contrast, has an albedo of only about 7 to 10%. It absorbs most sunlight and converts it to heat in the upper ocean. As Arctic sea ice melts, revealing darker water beneath, the Arctic absorbs more solar energy. This warms the ocean, which inhibits new ice formation the following winter and accelerates summer melting. The feedback effect is powerful. Satellite observations since the late 1970s show that Arctic sea ice extent has been declining at a rate exceeding 10% per decade. In September, the month when ice reaches its annual minimum, the oldest, thickest ice, which used to persist year-round for decades, is nearly gone. The ice that forms now is mostly thin, first-year ice that melts easily each summer. Scientists have run computer simulations projecting Arctic sea ice into the future under various emission scenarios. The results consistently show that the Arctic will be essentially ice-free during summer months, meaning less than 1 million square kilometers of ice remaining at least once before mid-century, possibly within the next decade or two. By ice-free, scientists don't mean absolutely no ice anywhere, but so little ice that the Arctic Ocean would be navigable, that we could sail ships directly across the North Pole during summer, something impossible throughout human history until recently. This transformation has implications beyond the Arctic itself. The jet stream, that fast-flowing river of air high in the atmosphere at the boundary between cold polar air and warmer mid-latitude air, is partly driven by the temperature difference between these regions. As the Arctic warms faster than lower latitudes, this temperature gradient weakens. A weaker jet stream becomes wavier, forming deeper meanders that can transport Arctic air far south or tropical air far north. These waves can also move more slowly across the landscape, causing weather patterns to persist longer. A heat wave that might have lasted 3 days becomes a week-long event. A rainstorm that would have moved through in a day stalls and drops extreme amounts of precipitation. Some research links this jet stream behavior to unusual weather events like the polar vortex intrusions that brought extreme cold to parts of North America, or the heat waves that have set records across Europe. The science is still developing, and not all scientists agree on how strong these connections are. But the Arctic's transformation is clearly capable of influencing weather far beyond the polar regions. In Siberia and Alaska and northern Canada, another dramatic change is underway in regions of permafrost, ground that remains frozen year-round. Permafrost covers about 25% of land in the northern hemisphere, underlying tundra, forests, even the foundations of buildings and infrastructure in Arctic communities. This frozen soil, some of it frozen for tens of thousands of years, contains enormous amounts of organic material, the remains of plants and animals that grew and lived during past millennia. Normally, cold temperatures lock this organic matter in place, preventing decomposition. But as Arctic temperatures rise, permafrost is thawing. What was solid ground becomes soft and unstable. Buildings built on permafrost begin to tilt as their foundations sink unevenly. Roads crack and buckle. Pipelines sag or break. Lakes form in depressions where ground has subsided. Forests of trees growing on thawing permafrost lean at crazy angles, creating what Alaskans call drunken forests. More concerningly, from a climate perspective, when permafrost thaws, the organic material locked within it becomes available to microbes that decompose it, releasing carbon dioxide and methane. Aerobic decomposition, occurring when oxygen is present, produces carbon dioxide. Anaerobic decomposition in waterlogged conditions produces methane. Either way, carbon that was stored in frozen soil for millennia enters the atmosphere as greenhouse gases. Scientists estimate that Arctic permafrost contains approximately 1,600 billion tons of carbon, roughly twice the amount currently in the entire atmosphere. Not all of this will be released, and the release will occur over decades to centuries, but even a modest fraction represents a significant addition to atmospheric greenhouse gases. This creates yet another positive feedback. Warming thaws permafrost, which releases carbon, which causes more warming, which thaws more permafrost. It's a cycle that, once started, tends to reinforce itself. All this melting ice, from mountain glaciers to Greenland to Antarctica, has a direct and measurable consequence that affects coastlines worldwide: rising sea levels. The measurement of sea level might seem simple, just measure the height of the ocean surface, but it's actually quite complex, because sea level varies with tides, waves, currents, atmospheric pressure, and other factors. What scientists track is mean sea level, the average height over long periods that smooths out these short-term variations. Since 1880, when reliable measurements began at tide gauges around the world, global mean sea level has risen by approximately 8 to 9 inches, or 21 to 24 centimeters. This might not sound like much, a handspan or so of additional water, but it represents an enormous volume of water added to the ocean. The ocean covers 360 million square kilometers of Earth's surface. Raising that vast area by even a few centimeters requires adding truly staggering amounts of water that comes from melting ice on land. In recent decades, the rise has accelerated. Satellite measurements, which began in 1993 and provide highly accurate global coverage, show sea level rising at approximately 3 millimeters per year on average, with some years showing faster rises. In 2023, mean sea level reached 101.4 millimeters above the 1993 baseline, the highest in the satellite record. In 2024, the rate of rise was 5.9 millimeters, unexpectedly faster than the 4.3 millimeters that scientists had anticipated based on previous trends. This acceleration is concerning because it suggests that ice loss from ice sheets is increasing faster than models had predicted, or that thermal expansion is progressing more rapidly, or both. Sea level is not rising at the same rate everywhere. Ocean currents, gravitational effects from ice sheets, regional wind patterns, and vertical land movements cause some regions to experience faster sea level rise than the global average. The Atlantic coast of the United States and the Gulf of Mexico are seeing some of the highest rates globally, in some locations exceeding 4 millimeters per year. Sea level rise comes from two main physical processes, each contributing roughly equally to the observed rise, though their relative contributions are shifting as ice loss accelerates. The first process is thermal expansion. This is a fundamental property of matter. Most substances expand when heated. Water is slightly unusual in that it's densest at about 4 degrees Celsius, and it expands whether warmed or cooled from that temperature. But the warming-driven expansion dominates in the ocean. As ocean water warms, the molecules move more vigorously, slightly more space, decreasing the water's density. The warmed water occupies more volume, even though its mass hasn't changed. The ocean has absorbed more than 90% of the excess heat trapped by greenhouse gases since the 1970s. This is an immense amount of energy, equivalent to exploding several atomic bombs every second, sustained over decades. The upper ocean, particularly the top few hundred meters, has warmed substantially. Even the deep ocean, below depths of 2,000 meters, where sunlight never penetrates and temperatures are near freezing, has warmed measurably. This warming throughout the ocean column drives thermal expansion that accounts for between 1/3 and 1/2 of observed sea level rise. The second process is the addition of water mass from melting land ice, the glaciers and ice sheets we've discussed. When ice that was sitting on land melts and flows into the ocean, it adds new water that wasn't previously part of the ocean volume. Between the 1990s and now, the relative contribution from ice melt has increased substantially. From 2006 through 2015, melting ice contributed approximately twice as much to sea level rise as thermal expansion. The accelerating ice loss from Greenland and Antarctica is making this imbalance even more pronounced. A third, smaller contributor is the net transfer of water from land storage to the ocean. Humans pump groundwater from aquifers for irrigation and drinking water. Much of this water eventually flows to the ocean through rivers, or evaporates and precipitates into the ocean. We've depleted many major aquifers worldwide, effectively mining water that was stored underground and transferring it to the ocean. This groundwater depletion contributes a small but measurable amount to sea level rise, perhaps 10 to 15% of the total. The impacts of sea level rise extend far beyond simply having the waterline higher on beaches. Higher baseline sea level means that storm surges associated with hurricanes and coastal storms reach farther inland. Coastal flooding that used to be rare becomes routine during high tides and storms. Salt water intrudes into freshwater aquifers, contaminating water supplies. Low-lying agricultural land becomes too saline for crops. Coastal wetlands, which provide habitat for fish and wildlife and buffer against storms, get squeezed between rising seas and human development, unable to migrate inland. Some of the world's most densely populated and economically important cities are coastal. New York, Miami, Shanghai, Mumbai, Tokyo, London, Amsterdam, Bangkok, Jakarta, Lagos. All face increasing flood risks. Small island nations like Tuvalu, Kiribati, the Marshall Islands, and the Maldives, which sit only a few meters above current sea level at their highest points, face existential threats. Some are already planning for potential relocation of entire populations, discussions that raise profound questions about national identity, sovereignty, and climate justice. Future projections depend heavily on how much additional greenhouse gas we emit and how ice sheets respond. Under a scenario where emissions continue at high rates and ice sheets collapse more rapidly than currently expected, models project that sea level for the contiguous United States could rise by 2.2 meters, about 7 feet, by 2100, and 3.9 meters, nearly 13 feet, by 2150. Even under moderate emission scenarios with substantial reductions, significant sea level rise is already locked in due to the thermal inertia of the ocean and the slow response time of ice sheets. Committed sea level rise, the rise that will occur even if we stopped all emissions immediately, is estimated at several tens of centimeters over the coming century. The response time of ice sheets is particularly uncertain. If warming melts ice sheets gradually and predictably, we might have centuries to adapt. But if tipping points exist where ice sheet retreat becomes rapid and irreversible, we could see much faster sea level rise with much less warning. Paleoclimate evidence suggests that during past warm periods, sea levels were significantly higher than today. During the last interglacial period, about 125,000 years ago, when global temperatures were only slightly warmer than now, sea levels were 6 to 9 meters higher. This suggests that current warming commits us to substantial sea level rise over the coming centuries, even if we stabilize temperatures soon. The question is how fast it will happen, and whether we can adapt to it. But the impacts of global warming extend far beyond melting ice and rising seas. Let's turn our attention now to the atmosphere itself, to the weather and the wild energy that courses through it. The atmosphere is not a passive blanket. It's a dynamic, turbulent system, constantly circulating heat and moisture around the planet. Add more energy to this system through warming, and it becomes more energetic, more volatile, more capable of producing extreme events. Heat waves have become more frequent and more intense. The definition of a heat wave varies by location, typically referring to a period of abnormally hot weather lasting several days. But the trend is unmistakable. Record high temperatures are being broken with increasing regularity. The years from 2015 through 2024 saw unprecedented heat globally, with each year warmer than historical averages. The dangerous aspect of heat waves isn't just temperature, but the combination of heat and humidity. The human body cools itself through evaporation of sweat. When humidity is high, sweat doesn't evaporate efficiently, and the body struggles to shed heat. Prolonged exposure to such conditions can lead to heat exhaustion, heat stroke, and increased strain on the cardiovascular system. Vulnerable populations, including the elderly, children, outdoor workers, and those with pre-existing health conditions, face the greatest risks. Cities experience heat waves more intensely than surrounding rural areas due to the urban heat island effect. Concrete, asphalt, and buildings absorb and retain heat more than vegetation and natural landscapes. On hot nights, when rural areas cool down, cities remain warm, depriving residents of relief. This can turn multi-day heat waves into public health emergencies. Droughts, too, are becoming more severe and longer-lasting in many regions. As temperatures rise, evaporation increases. Moisture leaves the soil faster. Plants transpire more, pulling water from their roots. Lakes and reservoirs shrink. The American West is currently experiencing what scientists call a mega drought, ranking among the worst in the past 1,200 years. Even after periods of heavy rainfall, the fundamental water deficit remains. Agricultural droughts affect crop yields. Ecological droughts stress forests, making trees more vulnerable to disease and wildfire. Hydrological droughts deplete water supplies for drinking, irrigation, and industry. All three types are becoming more common in regions already prone to dry conditions, particularly the Mediterranean, Southern Africa, southwestern North America, and parts of Australia. Wildfires represent one of the most visible consequences of warming temperatures and extended droughts. Fire has always been part of many ecosystems, playing a natural role in clearing underbrush and promoting certain plant species. But the scale and intensity of wildfires have changed dramatically. The wildfire season is now longer, starting earlier in spring and extending later into autumn. The area burned each year has increased substantially. Climate change contributes to wildfire risk in several ways. Warmer temperatures dry out vegetation, turning forests and grasslands into kindling. Earlier snowmelt in mountains means summer arrives with less moisture in the soil. Droughts create tinder-dry conditions that allow fires to ignite easily and spread rapidly. While factors like historical fire suppression policies and human development into fire-prone areas also play roles, the climatic contribution is undeniable. The smoke from these massive fires affects air quality thousands of miles away. In 2020 and 2021, smoke from western North American wildfires drifted across the continent, reaching the Atlantic coast and even crossing the ocean to Europe. This smoke contains fine particulate matter that penetrates deep into lungs, causing respiratory problems, exacerbating asthma, and increasing cardiovascular risks. The global mortality burden from wildfire smoke is estimated between 260,000 and 600,000 people annually, though this may now be an underestimate given the increase in extreme fires. Now let's consider heavy precipitation events, which might seem paradoxical in a discussion of droughts and wildfires. But remember, warmer air holds more moisture. For every degree Celsius the atmosphere warms, it can hold about 7% more water vapor. This means that when conditions are right for precipitation, storms can release significantly more water in a shorter time. The result is an increase in extreme precipitation events, the kind that cause flash flooding, overwhelm drainage systems, and trigger landslides. In the United States, the frequency of heavy downpours has increased significantly over recent decades. Rivers that historically flooded once every 100 years are now flooding more frequently. Flood risk maps based on historical data underestimate current risks, leaving communities unprepared. Flooding causes immediate dangers like drowning and property destruction, but also longer-term issues like contaminated water supplies, spread of waterborne diseases, displacement of populations, and economic losses. In 2024 alone, flooding affected millions across Central Europe, with devastating floods in Germany and Spain causing fatalities and significant economic damage. Hurricanes, or tropical cyclones as they're called in different ocean basins, draw their energy from warm ocean water. As sea surface temperatures rise, these storms have more energy available to fuel their intensity. While the total number of hurricanes doesn't necessarily increase, the proportion of major hurricanes, those reaching Category 3 or higher, is growing. Hurricane intensification is also becoming faster. In the past, meteorologists had days to track a storm as it slowly strengthened. Now, storms can intensify by 70 miles per hour or more within 24 hours, giving coastal communities less time to prepare and evacuate. Hurricane Helene in 2024 caused historic flooding across the southeastern United States, enhanced by exceptionally warm Gulf of Mexico waters. Hurricane Beryl earlier that summer became the earliest Category 5 hurricane on record, again fueled by unusually warm ocean temperatures. Rising sea levels compound hurricane damage through higher storm surges. When a hurricane pushes water toward shore, the baseline sea level is now higher than in previous decades, allowing storm surge to penetrate farther inland and flood areas that were previously safe. These extreme weather events don't occur in isolation. They interact and compound. A drought-weakened forest becomes more susceptible to wildfire. A heat wave, followed by heavy rainfall on parched soil, causes dangerous flash floods. A hurricane striking a coast already dealing with sea level rise causes far more damage than it would have decades ago. Scientists call these compound extreme events, and they're becoming more common. The Intergovernmental Panel on Climate Change, an international body of scientists that assesses climate research, has found with high confidence that human-induced climate change has increased the frequency and intensity of many extreme weather events since the mid-20th century. The evidence includes not just statistical analysis of weather records, but also attribution studies that use climate models to compare our actual world with a hypothetical world without human-caused greenhouse gas emissions. Time and again, these studies show that many recent extreme events were made more likely, more intense, or more prolonged by climate change. And yet, the impacts don't stop on land or in the atmosphere. The ocean, vast and deep, is absorbing much of the excess heat and carbon dioxide, with profound consequences for marine life. Oceans cover 71% of Earth's surface and contain 97% of the planet's water. They've been acting as a buffer, absorbing about 30% of the carbon dioxide humans have released into the atmosphere, and more than 90% of the excess heat trapped by greenhouse gases. This has slowed the rate of atmospheric warming, but at a cost to ocean health. When carbon dioxide dissolves in seawater, it undergoes chemical reactions that produce carbonic acid. This increases the ocean's acidity, or more precisely, decreases its pH. Since the start of the Industrial Revolution, the pH of ocean surface waters has dropped from 8.21 to 8.1. This might sound trivial, but pH is measured on a logarithmic scale, meaning this shift represents approximately a 30% increase in acidity. Ocean acidification, sometimes called the evil twin of climate change, creates serious problems for marine organisms that build shells or skeletons from calcium carbonate. This includes corals, oysters, clams, mussels, some plankton species, and many others. As ocean acidity increases, it becomes harder for these organisms to extract calcium carbonate from seawater and build their structures. Existing shells can even begin to dissolve in more acidic conditions. Coral reefs are particularly vulnerable. These magnificent structures, built over centuries by tiny coral polyps, support an astonishing diversity of marine life. About 25% of all marine species depend on coral reefs at some point in their life cycle, even though reefs cover less than 1% of the ocean floor. They also protect coastlines from erosion, provide food and livelihoods for hundreds of millions of people, and generate significant economic value through fishing and tourism. Corals face a double threat from climate change. First, ocean warming causes coral bleaching. Corals have a symbiotic relationship with microscopic algae called zooxanthellae that live in their tissues. These algae photosynthesize, providing corals with up to 90% of their energy. When water temperatures rise above certain thresholds for extended periods, corals expel their zooxanthellae, turning white or bleached. Without their symbiotic partners, corals can starve. If conditions improve quickly, corals can recover. But prolonged or repeated bleaching events lead to widespread coral decline. The second threat is ocean acidification, which impairs coral growth even if bleaching doesn't occur. Acidification particularly affects the thickening process that reinforces coral skeletons. A reef weakened by acidification is less resilient to storms, disease, and other stresses. The combination creates a scenario where reefs near the equator may experience severe annual bleaching within 15 years. While reefs at higher latitudes, though delayed from immediate heat stress, will face increasingly acidic waters by the time warming reaches them. There may be no safe haven. The Great Barrier Reef, stretching over 2,000 kilometers along Australia's coast, has lost approximately half its coral cover in the past 30 years. Similar declines are happening in the Caribbean, around Southeast Asia, in the Indian Ocean. By some projections, 90% of coral reefs worldwide could experience severe annual bleaching by 2055 if emissions continue at high rates. Even with drastic emissions cuts, many reefs face uncertain futures. The loss of coral reefs would cascade through marine food webs. Fish populations that depend on reef habitat for spawning and juvenile development would decline. Larger predators that feed on those fish would struggle. Entire fishing industries could collapse. Coastal communities would lose natural barriers against waves and storms, increasing their vulnerability to coastal erosion and flooding. But reef organisms aren't the only marine life affected. Ocean warming disrupts the distribution of species. Fish are moving toward cooler waters, often poleward or into deeper ocean layers. This shifts where and when fish can be caught, affecting commercial fisheries. Some species are moving faster than others, disrupting predator-prey relationships and the timing of seasonal events like spawning migrations. Ocean heat waves, prolonged periods of abnormally warm sea surface temperatures, have nearly doubled in frequency since the 1980s. These events can trigger mass strandings of marine mammals, harmful algal blooms, and shifts in plankton communities that ripple up the food chain. The ocean also faces decreasing oxygen levels as it warms. Warmer water holds less dissolved oxygen, and reduced ocean circulation due to warming limits the mixing of oxygen-rich surface waters with deeper layers. Many marine organisms, from fish to crustaceans to deep-sea invertebrates, require sufficient oxygen to survive. Areas with very low oxygen, sometimes called hypoxic or anoxic zones, are expanding in extent and severity. These changes are happening against a backdrop of other human impacts: overfishing, pollution, coastal development, and habitat destruction. The cumulative stress on ocean ecosystems is immense. Even if we stopped all greenhouse gas emissions tomorrow, much of the warming and acidification already set in motion would continue for decades or centuries due to the ocean's thermal inertia and the long residence time of carbon dioxide in the atmosphere and ocean. And yet, amid this catalogue of changes and challenges, there remains a crucial question. What can be done? What solutions exist? How can humanity navigate this transformation we've set in motion? The science on this is clear. To limit warming to levels that avoid the most catastrophic impacts, we must reduce greenhouse gas emissions dramatically and rapidly. The Paris Agreement, adopted by nearly every country in 2015, set a goal to limit warming to well below 2 degrees Celsius above pre-industrial levels, with efforts to limit it to 1.5 degrees. We've already warmed by about 1.2 degrees, and current warming is increasing at approximately 0.25 degrees per decade. Time is not on our side. Achieving these goals requires transforming our energy systems. About 80% of greenhouse gas emissions come from energy use, primarily burning fossil fuels for electricity, heat, and transportation. The solution lies in transitioning to clean, renewable energy sources that don't emit greenhouse gases during operation. Solar and wind power have emerged as the leading technologies. The cost of both has plummeted in recent decades. Between 2010 and 2020, solar photovoltaic costs fell by about 85%, and wind power costs dropped by approximately 55%. In many places, it's now cheaper to build new renewable energy facilities than to continue operating existing fossil fuel plants. Renewable electricity saved consumers $521 billion globally in 2022 by reducing demand for fossil fuels. Solar panels convert sunlight directly into electricity, with no emissions, no fuel requirements, and minimal maintenance. They can be installed on rooftops, turning every building into a potential power generator, or deployed in large solar farms in sunny regions. Wind turbines harness the kinetic energy of moving air, converting it to electricity. They work onshore and offshore, where winds tend to be stronger and more consistent. These technologies aren't without challenges. The sun doesn't always shine, and the wind doesn't always blow. Integrating variable renewable energy into power grids requires sophisticated management, energy storage solutions like batteries, and sometimes backup generation capacity. But these challenges are being solved through technological innovation and smarter grid design. Battery costs have fallen by 85% since 2010, making energy storage increasingly viable. Between 2015 and 2024, global renewable electricity capacity increased by about 2,600 gigawatts, a 140% rise. In the same period, fossil fuel capacity grew by only 640 gigawatts, a 16% increase. The trajectory is clear. Renewables are expanding rapidly, gaining market share and displacing fossil fuels. To meet the most ambitious climate targets, renewable energy capacity needs to triple by 2030. This is technically feasible and economically attractive, but requires sustained political will, supportive policies, and substantial investment. About $4.5 trillion per year needs to be invested in renewable energy and supporting infrastructure until 2030 to put the world on track for net zero emissions by 2050. This sounds enormous, but it's comparable to current fossil fuel subsidies, which totaled about $7 trillion in 2022, when including direct subsidies, tax breaks, and unpriced health and environmental damages. Energy efficiency is equally important. Using energy more wisely means we need to generate less of it in the first place. Simple measures like improved insulation in buildings, more efficient appliances and lighting, better industrial processes, and smarter transportation can significantly reduce energy demand. The goal is to double the annual rate of energy efficiency improvements from around 2% to over 4% by 2030. Transportation accounts for a large share of emissions, and the shift to electric vehicles is accelerating. Electric vehicles produce zero tailpipe emissions, and when charged with renewable electricity, they become truly zero-emission transportation. Battery costs have fallen dramatically, extending the range of electric vehicles and making them competitive with traditional gasoline cars. Many countries and regions have announced plans to phase out sales of new gasoline and diesel vehicles by 2030 or 2040. Beyond energy, agriculture contributes significantly to emissions through methane from livestock, nitrous oxide from fertilizers, and carbon dioxide from deforestation and land use change. Reducing these emissions requires a mix of strategies: improving agricultural practices, reducing food waste, shifting dietary patterns toward less emission-intensive foods, and protecting forests. Forests are crucial carbon sinks. Trees absorb carbon dioxide through photosynthesis, storing carbon in wood, leaves, roots, and soil. Deforestation, particularly in tropical regions, releases this stored carbon back to the atmosphere. About 10 million hectares of forest are lost each year. Halting deforestation and promoting reforestation and afforestation can remove significant amounts of carbon dioxide from the atmosphere while providing habitat for biodiversity, protecting water supplies, and supporting local communities. Some emissions will be difficult to eliminate entirely, such as those from certain industrial processes like cement production, aviation, and agriculture. To reach net zero emissions, these residual emissions must be balanced by removing carbon dioxide from the atmosphere. Natural carbon removal through forests, wetlands, and soil management will play a role. Technological approaches like direct air capture, which uses chemical processes to pull carbon dioxide from ambient air, and carbon capture and storage at industrial facilities, are also being developed, though they remain expensive and energy-intensive. International cooperation is essential. Climate change is a global problem that transcends borders. Greenhouse gases emitted anywhere affect the climate everywhere. The United Nations Framework Convention on Climate Change and the Paris Agreement provide frameworks for countries to coordinate their efforts, set emission reduction targets, provide climate finance to developing nations, and share technology and knowledge. Many countries have made commitments to reduce emissions. The European Union has pledged to cut emissions by 55% below 1990 levels by 2030 and reach climate neutrality by 2050. China, the world's largest emitter, has committed to peak emissions before 2030 and achieve carbon neutrality by 2060. The United States rejoined international climate efforts with targets to reduce emissions by 50 to 52% below 2005 levels by 2030 and reach net zero by 2050. Over 100 countries, representing more than 90% of global emissions, have set net zero targets. Whether these commitments are met depends on translating pledges into concrete policies and actions. Progress is uneven. Some countries are on track or ahead of schedule. Others lag behind. Current policies, if fully implemented, would limit warming to around 2.7 degrees by 2100. If countries meet all their pledges, warming could be reduced to about 2.1 degrees. Both scenarios exceed the Paris Agreement's 1.5-degree target, meaning stronger action is needed. Adaptation also matters. Even with aggressive emissions reductions, some warming and its impacts are already locked in due to past emissions and the inertia in the climate system. Communities must prepare for changes already underway, building seawalls and natural barriers against rising seas, developing drought-resistant crops, improving early warning systems for extreme weather, redesigning cities to handle heat waves and floods, and planning for shifting agricultural zones and ecosystem changes. The good news is that solutions exist. Renewable energy technologies work. They're becoming cheaper and more efficient. Electric vehicles are practical and improving. Energy efficiency saves money while reducing emissions. Natural climate solutions like reforestation provide multiple benefits. The transition to a low-carbon economy creates opportunities for innovation, jobs creation, and improved quality of life. The challenge is one of speed and scale. We know what needs to be done. The question is whether societies around the world will act quickly enough, decisively enough, and cooperatively enough to navigate this transformation. The answer will shape the world for generations to come. But let's step back from policy and technology for a moment and consider something more intimate: how climate change connects to the everyday rhythms of our lives. Weather shapes so much of human experience. The seasons mark time. Rain nourishes crops. Snow blankets the world in quiet. Heat waves slow afternoon hours to a drowsy crawl. For all of human history, people have lived within the bounds of familiar weather patterns, building cultures and livelihoods around predictable cycles. Climate change disrupts these patterns. Spring arrives earlier. Autumn lingers longer. Monsoons shift their timing. Snowfall decreases in some regions, while others see heavier snowstorms. Farmers who have planted by the same calendar for generations find it no longer reliable. Birds migrate at different times, arriving before or after the food sources they depend on. Plants bloom out of sync with the insects that pollinate them. These changes ripple through ecosystems in complex ways. A warmer climate doesn't simply shift everything uniformly. Different species respond differently. Some thrive in new conditions, others struggle. Relationships between species, predator and prey, plant and pollinator, host and parasite, can be disrupted when timing changes. Mountain ecosystems are particularly vulnerable. Many mountain species have nowhere to go as their habitat warms. They're already at high elevations. Further up is bare rock or snow. As suitable habitat shrinks, populations decline, sometimes to extinction. Similar dynamics play out in Arctic regions, where species adapted to cold conditions face disappearing habitat as ice and permafrost vanish. Permafrost, ground that remains frozen year-round, covers vast areas in the Arctic and high mountains. It contains immense amounts of organic material, plants and animals that froze thousands of years ago. As permafrost thaws, microbes decompose this organic matter, releasing carbon dioxide and methane. This creates yet another feedback loop. Warming thaws permafrost, which releases greenhouse gases, which causes more warming, which thaws more permafrost. Scientists estimate that permafrost contains twice as much carbon as currently exists in the entire atmosphere. Infrastructure built on permafrost is destabilizing as the ground thaws. Buildings tilt, roads buckle, pipelines crack. Communities across the Arctic face challenges maintaining basic services as the foundation beneath them literally shifts. These are not abstract scenarios in some distant future. They're happening now, measured in real time, affecting real communities, real ecosystems, real lives. And yet, they often feel distant when we're going about our daily routines, making dinner, commuting to work, watching television. The scale of climate change can make it feel overwhelming, incomprehensible, something too big for individual action to matter. But individual actions do add up. When millions of people make small changes, using less energy, choosing sustainable products, supporting clean energy policies, reducing waste, the cumulative effect becomes significant. More importantly, individual actions influence others. Choices become visible, conversations start, social norms shift, political will builds. There's something hopeful in recognizing that humanity caused this problem and therefore has the agency to address it. Unlike a meteor strike or supervolcano eruption, climate change isn't an external catastrophe beyond our control. It's a consequence of choices. Choices about energy, transportation, consumption, land use. Different choices lead to different outcomes. The future isn't written. Multiple pathways exist. We stand at a branching point in history. One path leads toward a world where warming exceeds 3 or 4 degrees, with catastrophic impacts on ecosystems, coastlines, food security, and human societies. Another path leads toward a world where warming is limited to less than 2 degrees, where renewable energy powers economies, forests expand, air and water become cleaner, and the worst impacts are avoided. Which path we take depends on decisions made in the coming years. It depends on governments implementing ambitious climate policies. It depends on businesses investing in clean technologies rather than perpetuating fossil fuel dependence. It depends on communities adapting and preparing. And yes, it depends on individuals making informed choices and advocating for systemic change. Throughout this journey tonight, we've explored how a few trace gases in the atmosphere can alter the entire planet's climate. We've seen how warming cascades through ice sheets and glaciers, oceans and coral reefs, forests and farmlands. We've traced connections between carbon dioxide molecules and hurricane intensity, between melting permafrost and methane release, between warmer air and wilder weather. The story of global warming is ultimately a story about interconnection. Everything touches everything else. The atmosphere connects to the ocean. The ocean influences weather on land. Weather affects ecosystems. Ecosystems cycle carbon. Carbon warms the atmosphere. It's a vast, intricate web where pulling one thread reverberates throughout the whole. This interconnection means that actions too have far-reaching effects. Planting a tree removes carbon while providing habitat. Installing solar panels generates clean electricity while reducing air pollution. Protecting a wetland stores carbon while filtering water and buffering against floods. Solutions often provide multiple benefits, co-benefits that extend beyond climate mitigation. There's beauty in this interconnectedness, even as it reveals vulnerabilities. Our planet is not a machine with independent parts, but a living system, dynamic and responsive. It has absorbed enormous amounts of heat and carbon, buffering the full impact of human activities. But that capacity is not infinite. Systems have tipping points where feedback loops amplify changes, where reversibility becomes difficult or impossible. We don't know exactly where all these tipping points lie. We know some have likely been crossed. Arctic summer sea ice may already be committed to eventual disappearance, even if we stopped all emissions immediately. Some coral reefs may not recover, but many potential tipping points can still be avoided with rapid action. The West Antarctic ice sheet's collapse is not inevitable. Amazon rainforest dieback, where drought and fire transform rainforest to savanna, can be prevented. Abrupt changes in ocean circulation patterns can be avoided. Uncertainty cuts both ways. Climate could be slightly less sensitive to greenhouse gases than current models suggest, buying humanity a bit more time. Or it could be more sensitive, with feedbacks accelerating warming faster than expected. Uncertainty is not a reason for inaction. It's a reason for caution, for taking out insurance against worst-case scenarios by reducing emissions. The science of climate change is robust, built on decades of observations, experiments, and theoretical understanding. Thousands of scientists across dozens of countries, studying everything from atmospheric physics to glacier dynamics to coral biology, have independently reached consistent conclusions. Human activities are warming the planet. The impacts are widespread and intensifying. Rapid emissions reductions are necessary to avoid the most severe consequences. This consensus doesn't mean every detail is known. Science is always refining, improving, discovering new mechanisms and feedbacks. But the core understanding is solid. Greenhouse gases trap heat. We're adding greenhouse gases to the atmosphere faster than natural processes can remove them. The planet is warming as a result. And so, we return to where we began, with sunlight streaming across space, warming our world, and with an atmosphere that has held that warmth close for billions of years, making this planet a home for life. We've changed that atmosphere in fundamental ways. We've thickened the blanket. The heat doesn't escape as readily as it once did. But just as we've changed it, we can change it back, or at least halt its further alteration. The tools exist, the knowledge exists, the potential exists. What remains is the collective will to act, to choose a path towards sustainability rather than crisis, to build a world powered by clean energy, where ecosystems thrive, where communities are resilient, where the climate stabilizes at levels that allow both nature and humanity to flourish. It won't be easy. It will require investment, innovation, cooperation, and sacrifice. But the alternative, the path of inaction, leads to a world with far greater costs. Costs measured not just in money, but in lives, ecosystems, possibilities. Perhaps the most important thing to remember is that climate change, despite its scale, is not separate from us. It's not something happening out there to an abstract environment. The climate is the air we breathe, the water we drink, the temperatures we experience, the weather that shapes our days. It's intimately connected to everything we care about: health, food, homes, communities, nature. When we protect the climate, we protect ourselves and the things we love. When we restore forests, we create beauty and habitat. When we transition to clean energy, we create jobs and breathe cleaner air. When we build resilient communities, we strengthen the bonds between people. The work of addressing climate change is, in many ways, the work of building a better world, one that's healthier, more equitable, more sustainable. And in the quiet moments, perhaps that's what matters most. Not the grand abstractions of global temperature anomalies and parts per million, but the simple experiences. A walk through woods that remain standing, a coast that isn't eroding, a garden that still blooms in familiar seasons, a sky where birds still migrate along ancient routes. The gift of knowing that the world we hand to the next generation is not diminished, but cared for. Tonight, we've traveled a long way together. Through the physics of greenhouse gases and the chemistry of ocean acidification. Through melting ice sheets and intensifying storms. Through coral reefs and permafrost. Through solutions renewable and natural. We've traced the story of how a few molecules in the atmosphere can alter the entire planet, and how human choices, small and large, shape the climate that shapes our lives. The night is quiet now. Perhaps you're feeling heavy with the weight of these realities. That's natural. Climate change can feel overwhelming, even frightening. But remember, too, that knowledge is the first step toward action. Understanding the problem is how we begin to solve it. Or perhaps you're feeling something else. Perhaps a quiet determination, a sense of possibility, a recognition that humanity has overcome immense challenges before and can do so again. We've eliminated diseases, built technologies that would seem like magic to previous generations, created international cooperation to solve global problems like the ozone hole. Climate change is a bigger challenge, certainly, but it's not insurmountable. Wherever your thoughts have wandered tonight, whatever feelings have surfaced, it's enough. You don't need to carry the whole world on your shoulders. You don't need to solve everything. You just need to do what you can, in the ways you can, with the resources and opportunities you have. And right now, what you can do is rest. Let your mind settle. Let the details fade into soft impressions. You've spent this time learning, thinking, engaging with complex and important realities. That takes energy. You've earned some peace. The earth will turn through another night. The sun will rise tomorrow. Wind will blow. Rain will fall. Seasons will cycle. Life will continue its resilient, adaptive, beautiful dance. And we, humanity, will keep working toward a future worth having, a climate worth stabilizing, a world worth preserving. You've done enough for today. You've listened, learned, perhaps felt something shift or deepen in your understanding. That's valuable. That matters. Now it's time to let go, to settle into the comfort of wherever you are, to close your eyes if you haven't already, and to allow sleep to come gently, like fog rolling in from the sea. The problems of the world will still be there tomorrow, but so will the solutions. So will the capacity for hope, for action, for change. So will you, rested and renewed, ready to face whatever the day brings. So, breathe deeply. Feel the weight of your body. Notice the softness of your pillow, the warmth of your blankets, the safety of your space. Let your thoughts slow down, become less urgent, drift like clouds across a summer sky. The story of climate change continues, but your part in it tonight is finished. You've shown up. You've paid attention. You've cared enough to spend this time understanding. That's no small thing. Now rest. Dream, if dreams come, or simply sink into that deep, restorative darkness where consciousness fades and the body does its healing work. There's nothing more you need to do, nothing you need to figure out, nothing you need to hold on to. Let it all go. Let yourself float, weightless, into sleep. Good night, dear friend. Thank you for being here. Thank you for caring about this beautiful, complicated, resilient planet we call home. May your dreams be gentle, your sleep be deep, and your tomorrow be full of possibility. Rest now. All is well. You are safe. You are enough. Sleep peacefully.